Okay, so this is number 6 on sapling, and it says this is our starting material. And you're not given the product, right? So you're not going to be able to you should still number your carbons, but you're not going to be able to say which bonds are broken, which bonds are formed, right? If you don't have the product, you can't do that part. But we still can number. So let's number 1, 2, 3, 4, 5, and 6. All right, so we can still number. We can't identify which bonds are broken, which bonds are formed. What's the other thing we need to do? What's the third step we always want to do? Every step we need to do what? Identify the electrophile and the nucleophile in each step, right?
Yes.
Yeah.
So in this case, which one's the electrophile? The H of the HCl. And the pi bond then is going to be the nucleophile. And so that's what attacks.
Can I ask you a question?
Mm-hmm.
Okay, so like for the HCl, it's above the arrow.
Yep.
So that's a solid.
No, so anything above the arrow is like a reagent. Things below the arrow are solvents. So if it's above the arrow, you want to use that first. If it's below the arrow, it's a solvent, which means it's in a lot of excess. Right? There's a lot of solvent around, right? The reagents on top, solvents on the bottom.
So do we ever work with the solvents?
Absolutely. Sometimes the solvents you'll see, we'll show you some examples in that workshop we did on Friday as well, has some, but we'll work some more tomorrow. But I'll modify this. I'll do this problem first, then I'll modify it by adding a solvent and see what it will look like then.
Okay.
Right, so reagents on top, solvents on bottom, solvents are in excess. First step, we broke the pi bond. And where's the plus charge going to be? Where should we put the plus charge? Why we want to put it on carbon 2, not carbon 1? Secondary versus primary carbocation, right? Now, is the secondary carbocation the most stable kind of carbocation there is? No. So if you could make a tertiary carbocation, would you? Yes. And so here, C3 here still has an H on there, right? We don't draw it in usually, but it's there. So what can happen is the electrons in this CH bond with the H can move over and attack the plus charge. So in this case, the nucleophile is this hydrogen, and the electrophile is that carbon, right? So now, where is the plus charge? On the tertiary carbon, which is carbon 3, right? And the Cl minus was along for the ride, right? We got to remember what's the fourth thing we always want to do? Balance our charges. So the Cl minus had to be there along the way too. So Cl minus is still in there. Now some people might ask, well, why doesn't the Cl minus react first? All right. Well, what's faster, an intermolecular reaction or an intra? Within one molecule, intra is usually faster. Right? So intra will happen faster. Right? So then the final step, what's my electrophile is my nucleophile? Cl is nucleophile. All right. Good. So the final product in this case is this. Right. The tricky part here was this hydrogen shifting, this hydrogen moving. Right? Why did it move though? Because it went from a secondary carbocation to a tertiary carbocation. That's more stable. You always move downhill. All right. Now, let's pretend for an added layer, let's say we were doing this reaction in water. There's water below the arrow like that, H2O below the arrow. Now, if it's below the arrow, that means there's an excess of it. It's a solvent. Right? So that's going to react more. It's going to be more likely to react than even the Cl minus. Even though, right? So if I draw water in here, since it's a solvent, there's a lot of it. Right? Maybe there's 100 waters for every one Cl minus. Which one's the better nucleophile, Cl minus or water? Cl minus is the better nucleophile, right? It's more electron rich. But is that all that matters for reactions? concentration matters, right? There's a lot more water around, it's more likely to react. So one other thing that could happen is if you let me draw this another way. Water could have attacked. Five, 6, and Cl minus is still there, right? So this is pathway 1, no H2O, right? That's the product. If was water around, the HCl would have grabbed that last H, the electrons would have gone to the oxygen, and we'd have made an alcohol and HCl. Right? The hard step still is this hydride shift, right? The intramolecular hydride shift is the key. And then it's just a matter of if you have whatever you were dealing with, right? If you're in a solvent, then the solvent's more likely to react. If there was no solvent, Cl minus more likely to react. Yep.
So is it always that case for the solvent?
Yeah.
If it's going to react, we just do that step first, and then.
You always react the stuff up top first, right? The reagents up top first, and then if there's solvent around, right? Then it's just a matter of concentration. There's a lot more of this around. Everybody see how we regenerated HCl here too? I mean, really? Or if anybody takes a step back, so something you learned in Gen Chem, if you just had HCl and water in a beaker, what do you end up making? What exactly do you end up making? H3O plus and Cl minus, right? So this first step could have been reacted with H3O plus, right? So don't forget what you know, right? HCl is a strong acid. Strong acids fully dissociate. Okay? Other key thing is this step here, right? Balancing our charge along the way. The Cl minus grabs that, and actually HCl can be a catalyst in some of these cases with water. If you go back and look at the problems we gave you on Friday, there's a couple examples like that too. This is number 7. HCl. Okay. The other big thing I think people don't, right? I mean, their hints are usually pretty good. Sometimes the hints are helpful here, right? To see what happens. Okay. First step, we can't identify bonds, broken bonds formed, but we can number the carbons, right? So always number your carbons. Right? First step, what's my nucleophile? What's my electrophile? Nucleophile is the pi bond. The H is the electrophile. Where do we want to put the plus charge? Carbon 1 or carbon 2?
Or the H goes on 1.
The H goes on 1 and the plus charge goes on 2. And we do that because that would be the most stable carbocation. Right? Now, a little bit of a trick here. This is a challenging problem. What do you guys know about 4-member rings?
They're not angle strain.
Angle strain, right? What's the hybridization state of carbon 3?
SP3.
So it's sp3. What's the bond angle of an sp3 hybridized carbon? 109.5. What's the bond angle of a square? 90. So is that thing strained? Yes. So does it want to be in a 4-member ring? No. So what will happen is the bond between 3 and 4 will attack the carbocation. You'll open up the ring. So here's carbon 1. So what new bond did we just form between which two elements? Or which two carbons got new bond? Have a new bond? 4 and 2. good. So there's 2, there's 4, 5, 6, and 3. So we've done that, numbered our carbons. Did we balance our charge? No. So where's the plus charge at now? Who lost electrons? Who lost a bond?
3.
3 did. Everybody see that? The plus charge is now on 3. Right? Not to mention Cl minus again has been along for the ride the whole time. Right? So we've done a ring expansion because we don't want to form a ring. So even though this is a secondary carbocation and this is a secondary carbocation, right? You think that's a sideways move, but if you can open up a strained ring, it's okay. Right? So to open up a ring, it's okay to go from secondary to secondary. Normally, it is not okay to go from secondary to secondary. Right? You always got to go downhill, unless you're, in this case, relieving ring strain. So in the final step, nucleophile, electrophile.
Wouldn't the plus move over to 2?
Nope. Ooh. Good catch. Good catch. Can we make a better carbocation? What about the H here on carbon 2? It could do a shift over. And now we'd have what kind of carbocation? A tertiary carbocation. And where's the plus charge at? On 2. Cl minus is there. Now we're done. Good. Now, these problems are hard, right? They'd be a lot easier if I gave you the products. So we will give you problems where we give you the products for sure, right? But you know, not all of them will be that way.
I think the hardest ones are where you give us the products and then we have to do oh, that's a little bit.
Which ones? Work backwards?
Yeah.
And no start materials? Yep. So there's another way, right? Another way to ask problems too is to give you the products and say where do the start materials come from, right? But then you got to realize, right? I mean, you could have looked at this, and you could have said this came from there being a pi bond between 1 and 2, and that'd been right. That'd be okay. You could have said this came from a pi bond between 3 and 2. That'd also been right. Right? Or this is a little harder. Right? So a lot of times when you're working backwards, you can have there's different options. There's more than one option too. So for number 9, they're saying draw the structures of 2 stereoisomeric alkenes that would give 3 hexanol as the only major product of hydroboration followed by treatment with H2O2. So we haven't talked about this reaction in class yet, but they're saying you're getting this. They're saying what alkenes could it come from? When they say stereoisomeric alkenes, what do they mean? So alkenes have stereoisomers. What are the stereoisomers of alkenes? Cis and E and Z, right? E or Z or cis and trans, right? So that's what they're saying, right? Would it matter if I used a Z alkene here or a cis or an E alkene to get this product? No, it wouldn't. All right. So again, let's number 1, 2, 3, 4, 5, 6. So if we only want to get, right, the alcohol, right? Notice this molecule is symmetrical, right? This is right. You could split it down the middle. 1, 2, 3. 1, 2, 3. We have to imagine, right, where would the double bond be at to only get 3-hexanol? Right, where would the double bond be at to only get 3-hexanol? Where would we want to have a pi bond to only get 3-hexanol? So you should be thinking, right, well, I know carbon 3 has to be part of a pi bond, right? Because that's where the functional group ended up. So you can either go one of 2 ways. You can have a pi bond here or have a pi bond here. So let's just draw those. Now I just drew the E or Z version of these. Both of them I drew the Z. But the E would also be equally possible here, right? See that? I could draw the E of this version and the E of this version too. Okay? So now which one of these will only give me that product? So if I looked at these as A and B, only one of these alkenes will always just give me this. Always just that. Which one is it, A or B? B. B will always give me this one here. With A, I could also, right, if I'm forming a carbocation, could I form a carbocation on 2 and 3? Are they both equally as likely? Yes. I don't want to have an OH on 2. But now here, I could form a carbocation on 3 or 4, just as likely. But notice 3 and 4 are basically the same when you end up putting the function group on there. All right, so the answer is B, both the E version here I've drawn, and the, let me see if I can do it, Z version as well. Yep. So that's the answer they're looking for. They're doing a new reaction, hydroboration, where you can add an OH with boron. That's like one of the last ones we're going to learn tomorrow. So number 19, this reaction involves something called ozonolysis. So step 1 is O3, step 2.
I did Google this and read about it, and it was really even more confusing, all the mechanisms.
But it's not asking for the mechanism. So this is not, yeah, so we're not going to ask you for the mechanism for this. We're going to want you to know what the products would be, but we're not going to ask you for the mechanism.
Oh, or are you talking about in general or just for
Just in this problem. Right? So basically what O3 does, what ozonolysis does, it takes alkenes and cuts them in half. Think about a pair of scissors cutting them in half and turns them into carbonyls. Right? So if I number these carbons 1 and 2, what you end up with as 2 products. So where there was a double bond, both sides now become carbonyls. And it does not affect these aromatic rings. Keeps those the same. So that's all there is to it. 1 and 2. So you split that double bond, cut it right in half, and you get 2 carbonyls. That's all ozonolysis does. Don't worry about the mechanism. That's all you need to know, is that O3 cuts that in half, right, and gives you 2 carbonyls. All right, let's do number 20, which is basically taking this reaction and working backwards. And it says this is our product. There's ozone, step 1, and there's dimethyl sulfide is step 2. But in this case, you're really not worried. I mean, if you see O3, all you need to know is that what it does to alkenes. It cuts alkenes in half and turns them into 2 carbonyls. That's what you need to know. So now if you're looking at this and you see 2 carbonyls, these 2 carbonyls must have they were together at some point, right? There's 2 carbons. So let's number the carbons like we should always do. 1, 2, 3, 4, 5, 6, 7. So in this case, which 2 carbons formed a double bond before? 3 and 7, right? So let's just draw 3 and 7. Now 7 was also bonded to 6, which was bonded to 5, which was bonded to 4, and 4 was bonded to 3. What else is 3 bonded to? 2 and 1. 2 and 1. So that's the starting material it came from. And that's how I would go backwards and work and find the thing. Right? So it looks a lot worse than it is, right? This is not hard.
I did it the long way.
Right.
I actually used the ozone.
Yep.
All that.
Just find out where the double bond came from. That's where you connect those pieces together. The hardest part, where people are going to screw this up, is they're going to forget carbons 1 and 2. They're not going to number people won't number their carbons, and they'll mess up. They'll lose a carbon or gain a carbon somewhere along the line. That's what the problem will be. So 2 more reactions to learn. One is actually really easy. One is a little more complicated. The easy one, let's say you have this. And you'll see H2, and you'll see below probably palladium on carbon. All right, so this is called a hydrogenation. Essentially a way to add hydrogen to alkenes, to reduce alkenes. And the products you'll get here the H's will add, and they always add cis. So it's a cis addition across the pi bond. All right? So the H's always add on the same side, like a Lego clicking in. Right? Like a Lego clicking in. All right? The H's just add in. And the mechanism for this isn't really known. The palladium helps get the hydrogen in place, and it adds all on one side. Right? So the hydrogens add on one side. So what does that mean? Cis addition, so they're always on the same side. Does that mean there's a carbocation ever?
No.
No carbocations then. Right? So I think making a reaction sheet with all these kind of tidbits of information is good. Right? So bromonium ions, do they have carbocations? No. Right? Knowing which ones have carbocations. So if you don't form a carbocation, can you do a rearrangement? No. Right? But always be wary of those things. So bromonium ions, because you don't form a carbocation, you always get what kind of addition? Not a cis addition, you get a trans addition with bromonium ions. Right? You get a trans addition. Yep, Cl2 is the same thing. Chloronium ion versus bromonium ion, same deal. All right, so that one's easy enough to know. Right? This one. The other one is somewhat similar. Gives you a little different product. So it would be BH3, and then that's usually step 1, and then step 2 is OH minus or H2O2. Now the end result for this is also a cis addition. You also get a cis addition. There's no carbocation here either. So cis addition. No carbocation. There's another little tidbit of complexity here that I haven't mentioned yet. But I just want to get this first part done. Cis addition, no carbocation.
Wouldn't the BH3 have been one that's going on there?
Yep. So yeah, I haven't got to the mechanism yet. Yep, so we'll show that. But I just want to know that this is what the products are, right? Cis addition, no carbocations. Okay, so now let's go through the actual mechanism. But I'm gonna change my starting material a little bit. I'm gonna make my starting material an unsymmetrical alkene. Alright, so first thing we do, number the carbons. OH minus, H2O2. Now this is where it gets different, right? If you took H plus in water, where would you end up with where would the OH end up? If you took H plus in water, where would the OH end up? Would it end up on carbon 2 or carbon 7? If you took H plus in water, where's the OH going to end up? Maybe we're not ready for that then. I'll show that after I show this example then. Let's see where the OH, right? Because again here, the OH is either going to end up on carbon 2 or carbon 7, right? But with BH3, we actually end up with the OH on the less substituted carbon. You should recognize that as being opposite of what we've been getting with, right, HCl and all those things, right? The group we're adding always ends up on the most substituted carbon, right? Because it came from the most substituted carbocation. But, right, no carbocations here. So there would be an H. There would be an H coming up, and the OH is there. Right? So the OH ends up on the less substituted carbon of the pi bond, which is just the opposite of where it's been ending up with HCl in water, right, or H plus in water. See that? So one of the terms, if the group that you're adding ends up on the less substituted carbon, so if the functional group ends up on the less substituted, it is anti-Markovnikov, anti-Mark. The product is an anti-Markovnikov product. That's what we call it. The functional group ends up on a less substituted carbon. We call that anti-Markovnikov. Some Russian guy got these products named after him. So all we're looking at is an end product. If the function group ends up on the less substituted thing, it's anti-Markovnikov. If it ends up on the more substituted thing, what is it then? Then it's Markovnikov, right? But all this has to do with is the products. All right, all we're looking at is the products.
This might be a really stupid question, but what happened to the BH3?
Right, the BH3 did not end up in the product. Very good. That is true.
They just go away.
Yes, the BH3 adds, and I'll show you the mechanism in a second. It adds, and then the OH minus replaces it, actually. Right. So we'll go through that mechanism right now. Let's go through this mechanism. Right. So we know it's a cis addition. There's no carbocations. And we know the functional group, the OH in this case, ends up on the less substituted carbon, which is completely different than everything else we've been doing. Right? The functional groups have always been ended up on the more substituted carbon for all these other ones. Right, so it's on the less. So what happens here? So what happens, you guys know about BH3. Is BH3 going to be an electrophile or a nucleophile in this case?
Electrophile.
It has to be the electrophile. Now why is it an electrophile? How'd you know it's electrophile?
Incomplete octet.
BH3 doesn't have a complete octet, does it? It has an empty p orbital. So it has these H's. It's sp2 hybridized. So what's going to happen here, this is all going to happen at once, the pi bond is going to go for that empty p orbital. And at the same time, this hydrogen is going to go to carbon 2. Right, so there's the BH2 now, right, on carbon 7. 1, 2, 3, 4, 5, 6, 7. Right? So why would it want to do it this way? Well, there's a couple reasons probably, right? This boron, right, this carbon 2, is there more stuff on carbon 2? Is it more sterically bulky? Is there more stuff on carbon 2? It's more substituted, right? So the boron would rather get away from it, right? So the boron is going to go to carbon 7 instead. But notice now the boron's on the less substituted carbon. The functional group added to the less substituted carbon. No carbocation, no carbocation, cis addition, right? It added across the same side. Could it added across the top too? Yes, right? I'm just showing one way it added. It could have also came from the top, not just from the bottom. So now the BH2 is there. And the last step, right? All you need to know is that when you put the OH minus in here, it replaces the BH2 with the OH minus on this, and it stays. Everything stays the same. Just swap out the groups. That's all. You need to know this mechanism, but this step you don't need to know. So what's the keys here? Cis addition, no carbocation. You get this anti-Markovnikov product because the functional group ends up on the less substituted carbon. So that's the last reaction I needed to show you. So sometimes they'll be like B2H6, or they'll have, if you see boron with a hydrogen on it, it's doing this. Don't worry about all sorts of fancy weird reagents. If you see boron, it's doing this hydroboration. So there'll be B2H6, there'll be BHB pin sometimes, who knows. It's just doing this, the same idea. We'll always draw it as BH3. But if you see it differently, that's all it is just doing the same thing. Cis addition, no carbocation.
What is this called again?
This is called hydroboration. Hydroboration. Right, you're adding an H and a boron, which eventually gets replaced with an alcohol, OH. Cis addition, no carbocation.
So you say cis addition, it's like whatever is adding on is always adding on the
Same side. They're always on the same side. Same side. Cis addition. Right? Bromonium ions, they give you a trans addition. Carbocations give you what? A mixture of both cis and trans. 27. This one involves bromonium ions. This is nice because it also takes into account thinking about the stereochemistry you're creating when you do these things.
What does the CCl4 indicate for this one?
So, what does it say?
It says Br2, CCl4.
CCl4 is a solvent. So I must have a little different one than your 27, but.
It's just on the top of it.
Oh, okay.
So I just thought that they were both.
That's a solvent. CCl4 is a solvent. It's actually an ozone depleter. It's a really bad solvent. You can't use it anymore.
Oh, yeah.
Carbon tetrachloride. Yep. So don't worry about that. CCl4 should be on the bottom. It's a solvent. But anyways, right, you've seen, I told you, right, if bromine or chlorine's bonded, they're not nucleophiles or they're really electrophiles usually. There's nothing going on with them. So Br. So here we go. 1, 2, 3, 4, 5, 6. Number our carbons, always number our carbons. Identify the electrophiles and nucleophiles. So the electrophile here is going to be the bromine, right? One part of the bromine is going to be delta plus, it'll be delta minus. Pi bond attacks, breaks the carbon-bromine bond. But then the weird part is that the bromine clamps back down. So you attack the bromine, break the bromine-bromine bond. But then this lone pair comes back down because when we have Br2, do we form carbocations? No. So we don't want to form a carbocation.
That's why.
And that's why. Now the bromine, right, I just show it coming out. Could it have also come from the bottom? It could have, right? So you can get both enantiomers in the top or the bottom, right? This pi bond is sp2 hybridized, right? You use carbon, so it's flat. So it could have attacked from the top or it could attack from the bottom. It doesn't matter. So here, the last part, bromine attacks from the backside, right? Because we always get a what kind of addition? For this, we always have a trans product, a trans addition. So one bromine's coming up, and the other bromine's going away. I think they ask you to draw in the H's, so you have to draw in the H's too. There you go. All right, so you always get the trans. Now, a good thing to try would be to go through and label this RNS and this RNS and realize you'd make the enantiomer as well, the exact opposite. Right? So if this 3-membered ring was wed or was hatched, you get the exact other enantiomer as well. Right? So you're going to make, in this product, you're going to make a mixture of enantiomers, right, called the racemic mixture, 50-50 mixture of the same two things. So let's look at number 31. This involves our H2 palladium on carbon. Sometimes there'll be platinum too, but the question here is what products we make, right? So we know from before this is a cis addition, right? Cis addition. The H is added from the same side, right? You don't really know the mechanism for this one, but you know it's a cis addition, and it always reduces pi bonds, right? We add H's to pi bonds. So again, let's number our carbons: 1, 2, 3, 4, 6, 7. 8, 9. So where are we going to add H's to? Where are we going to add them to? The pi bond. So the pi bond between 1 and 2 is going to be gone. All right. So we added H's over here. But are we making stereo centers when we add those H's? Or are we making asymmetric centers? Because there already were H's here, right? So if I add another H there, am I making it an asymmetric center? No. Right, that's the trick. That's one of the tricks. But now if I add H's here, am I creating a stereo center at asymmetric center at those carbons? Yes, I am. Right? That means they're RS. And so that's what they're kind of asking you here. They're asking you, first of all, I want you to draw the two possible products. So what are the two possible products? All right, let's just draw 2 of these out. So what do we have to make sure is the same? The H's have to be what? On the same side, right? Always. Because it's a cis addition. So in one case, we could have them both be wedges, and that means the other thing's hatched. Or in this case, the H's would both be hatched, and the other pieces would be wedged. So you get a 50-50 mixture of both of these, right? 50% of this, 50% of this. Right? You get a 50-50 mixture of both of these. So what are these to each other? What's their relationship? You form a racemic mixture, but what's their relationship to each other? These two isomers are what to each other? Well, if you don't know, you can always find out the stereo center, right? So figure out the stereo centers. All right, so we can do all that, blah, blah, blah. We figure that out. These are actually enantiomers to each other. Everything is opposite. And because they're a 50-50 mixture of enantiomers, we call that racemic.
They'll always be enantiomers of each other, no matter what it's reacting with.
And well, if you're making asymmetric centers like this with H2, you will always make enantiomers, unless there's another stereo center in the molecule, right? So we could have threw a curveball at you, right? If I had a stereo center here that was R, and we did this reaction, what would I make then? Not enantiomers, but I would make what? Diastereomers, right? If they had one stereo center in common, if I put there's something at 7, I put a carbon at 7 and made that R, then they'd be a pair of diastereomers, not a pair of enantiomers. There was still carbon. There's 2 hydrogens on this carbon, right? It started out with 1 on each carbon. Carbon 1 had 1 hydrogen. Carbon 2 had 1 hydrogen. But then in the reaction, they each got another one. But the result, 1 and 2, are not asymmetric centers, right? Because they have two of the same things bonded to them. So that's why you don't, I mean, you still reduce that double bond, but you're not worried about R and S because it can't be R and S. So when you do these reactions, you have an excess of H2. There's always there's an excess of H2, right? So yeah, so yes. So you're looking at it and saying, well, how could I have added H2 twice? Because you have an excess of H2.
And that's always true.
That's always true with H2. Yes, it's always true.
Just H2?
Just H2. Unless we say excess. We could say, I mean, I could put 1 atmosphere, which indicates like, it's like almost like that's an excess. It's a gas, right? So there's a lot of molecules up there. But yes, H2, it will reduce all the pi bonds. Just assume you have a lot of this.
And
it's an excess.
Means what?
Racemic means you have a 50-50 mixture of enantiomers. Racemic is a 50-50 mixture of enantiomers.
If they're diastereomers, then they're not.
They're not racemic. If they're diastereomers, they're a whole other thing. They're just diastereomers. But when you have a 50-50 mixture of enantiomers, that's a racemic mixture, they call it. Racemic only refers to enantiomers. 50-50 mixture of enantiomers.